Hello and welcome to a presentation for the ME 4056 Refrigeration Lab. My name is Kevin and my team members are Ben and Miguel. This is Team 4 in Section L02 and we will present our current status in the study of a vortex tube cooling system. This team, representing Burdell Incorporated, has been requested by the client Machine Chillers Incorporated to analyze the performance of their vortex tube cooling system. The goal is to independently review the system for the client by modeling it and determining its characteristics via testing. This testing will be split into a steady-state analysis and transient analysis, and the steady-state portion will be discussed in further detail here. In the study, the setup shown in Figure 2 uses the following pieces of equipment: a pressurized air source, heat exchanger, accumulator tank, vortex tube, aluminum load, insulation, and sensors for pressure, temperature, and volumetric flow. At a high level, compressed air is fed through a heat exchanger and vortex tube, where the cold air is sent to cool the load and hot air is rejected from the system. Temperature is measured at each station, pressure is measured at stations 3, 4, and 5, and flow rate is measured at the hot and cold air outlets. Before performing the analyses, it is first necessary to determine system offsets. The sensors in the setup are not perfect and may produce values that are slightly off from what they should be. In order to counteract these offsets, they are subtracted from the sensor readings later in the study. Steady-state analysis will begin with the characterization of the motor compressor and vortex tube components, specifically defining the relationships between voltage and air pressure, as well as temperature and mass flow with respect to pressure for both the hot and cold streams. Both steady-state and transient analysis will involve the study of the refrigerated load, as the thermal resistance and heat exchange rates will be calculated for each case. Likewise, both analyses will include an uncertainty analysis to assess the validity of the experiments and the trustworthiness of the results. First, to calculate offsets, the ambient conditions and ambient sensor values must be known. At ambient conditions, the temperature should be 21.1 degrees Celsius, pressure should be 1.018 bar, and mass flow rates should be 0. The ambient sensor readings were determined with the compressor turned off, and the known ambient values were subtracted from these readings in order to determine the offsets, which are shown in the table below. Subscripts C denote the cold stream, subscripts H denote the hot stream, and numerical subscripts denote the station number.
Following the collection of ambient data and subsequent calculations of the offset, our team proceeded to conduct tests with varying input voltages ranging from 0 to 2.5. The resultant input voltage to pressure relationship at stage 3 is presented here. Our findings indicate a correlation between an increase in input voltage and an increase in pressure. Furthermore, the system appears to exhibit a diminishing rate of change in pressure with an increase in input voltage. However, it is worth noting that the pressure reading corresponding to 2.5 volts does not conform to this trend. This anomaly can be attributed to the recollection of faulty data collected in our first round of testing. This change may be a result of alterations in the testing environment, such as the atmospheric pressure or possible system leaks. In order to determine the behavior of the vortex tube, the relationship between the temperature of the cold stream and its mass flow rate to the same pressure values that were stated previously was experimentally determined at the varying input voltages. Our findings indicate that as the pressure increases, the temperature of the cold stream decreases, while subsequently its mass flow rate increases. We have included these relationships for visualization below. The same procedure was used to determine the impact of the pressure on the hot stream. The opposite of the cold stream temperature occurred, resulting in an increase in temperature as the pressure increased. However, the mass flow rate also subsequently increased. A visualization can be shown here.
With no heat being absorbed by the load as it is at a constant temperature when in steady state operation, from an energy balance it can be concluded that the heat transfer rate from the cold air to the load is equal in magnitude to the heat transfer rate between the load and the surrounding ambient air. With that in mind, the heat rate through the cold stream of air was calculated according to the following equation, and then, after calculating the theoretical insulation value, the heat rate through the insulation was calculated. The results will allow us to determine how accurate the theoretical thermal insulation resistance model is. As can be seen from the data, the heat rate through the cold stream of air and the heat rate through the insulation did not match within the experimental uncertainty bounds. This indicates that the theoretical thermal insulation model cannot accurately quantify the thermal insulation. Possible causes for this discrepancy are that the theoretical model assumes a constant insulation thickness around all surfaces of the load, but in reality, the top surface of the load is not covered by insulation, and there are gaps in between the surfaces of the insulation through which air can be passing through and transferring more heat through convection. Additionally, the theoretical insulation model considers only a linear resistance calculation, without taking three-dimensional effects into account, which can have significant impacts on the drawn results. Knowing that the theoretical insulation thermal resistance value is not an accurate representation of the system, the insulation thermal resistance was calculated experimentally by setting the heat rate through the air and the heat rate through the insulation equal to one another. After rearranging terms, this led to the shown equation for the experimental insulation thermal resistance. For each of the tested voltage inputs, the experimental insulation thermal resistance was calculated and compared to the theoretical one. As can be seen, the experimental and theoretical values do not match within the experimental uncertainty bounds, as could be expected from the previous results. Additionally, the experimental insulation thermal resistances do not match with one another from one trial to another. This indicates that unmodeled factors could be affecting the system, such as other forms of heat transfer including radiation and convection, and that the capabilities of the sensors to measure the necessary physical quantities for the calculations is not accurate enough to allow for a proper quantification of the system parameters. Assumptions such as treating air as an ideal gas and using constant specific heat for this substance can also have unaccounted for impacts that can be leading to the deviations in the results. Moving into our conclusions, a summary of our results includes the development of the relationship between motor input voltage and the incoming air pressure to the refrigeration system, and an analysis about the relationship between temperature and mass flow rate with respect to pressure for both the hot and cold air streams of the vortex tube. Additionally, the theoretical insulation thermal resistance model was analyzed, and an experimental model for the insulation thermal resistance was derived. As key takeaways of this analysis, we have that the theoretical insulation model is unable to accurately represent the physical system within the experimental uncertainty bounds. The experimental result for the insulation thermal resistance is also not maintained across the trials. This indicates that the assumptions, derivations, and sensor capabilities must be re-evaluated to properly quantify the system. This leads us to our next step, in which the team will perform a transient study of the system to understand its behavior with respect to time. This will involve recollecting offset values, assessing the system's response to an input pressure of 40 psi from the compressor and to an input pressure of 80 psi from the building's air supply. Then, an energy balance calculation will be performed, and the mathematical validity of the theoretical model will be evaluated considering the experimental uncertainty calculations. With knowledge of both the steady state and transient responses with different system inputs, the team can successfully characterize the system for its client. We'd like to thank you for your time, and please refer to our appendix for the equations used in this analysis and to our references section.